Hello everyone, my name is Abhishek Joshi and I am excited to present our research title, a multi-model transformer architecture, combining sentimental dynamics, temporal market data, and microeconomic indicators for study stock return forecasting. This work has been selected in IEEE Big Data for the workshop of IEEE International Workshop on Large Language Model for Finance. The co-author for this paper is Janvi Krishna Koda and Dr. Alihan. The aim of our research is to improve stock market forecasting by integrating dynamic graphs, sentimental analysis, and state-of-the-art graph neural network. I'll be taking you through the challenges in stock market prediction, our proposed solution, experimental setups, results, and future directions. So, coming back to the introduction, stock market prediction has always been a challenging problem due to the intrinsic complexity of financial market. Market is highly dynamic, influenced by economic factors, several interdependencies, and investor sentiments. Traditional models that are there in the market, such as ARIMA, GARCH, LSTM, they solely rely on historic data and fail to account for these complexities. Their limitations are especially evident during the turbulent market conditions. So, to address these challenges, our study proposes a novel approach that combines graph neural networks with the sentimental analysis and dynamic graph representation. By doing so, we aim to enhance the accuracy and the robustness of the stock market price prediction. For the problem statement, our objective is to design a predictive framework capable of capturing temporal dependencies from the historic stock data, reflecting evolving relationship among stock using dynamic graph. We are leveraging sentimental analysis to incorporate market sentiments into predictions. Now here, the main problem is the traditional model fails in several key areas. They struggle to incorporate multidimensional data such as temporal relationship and sentiment-driven feature. Static graph, which many model uses, cannot adapt to rapidly changing market condition. Moreover, stock prices are influenced by microeconomic indicators, sector-wide trends, and investor sentiments, all of which impact in complex and non-linear way. By addressing these limitations, our framework provides accurate prediction for both stock market prediction and their bidirectional movement. So for the mathematical formulation, I'll walk you through the formula that is PT1, which is a function of MTWT, DS, HS, GS, and ES, where our PT plus 1 is the predicted price for the next day. MTW, this represents a series of historical market data for the stock, for any given stock in a question over the path of any W days. Now, DS is the description of the stocks, HS represent the stakeholder information, and GS is the graph embedding derived from dynamic graph. So the core problem here is traditional model often fail that we are trying to resolve with our novel approach. We have expanded our problem solution into four different ways. We have integrated graph dynamics to reflect evolving stock relationship. We are capturing temporal dependencies from the historic data. Along with that, we are leveraging sentimental analysis to incorporate quantitative market signal, which result into an accurate stock price prediction and their bidirectional movement for the forecast. For our given proposed model, it consists of three core components. So the first one is the dynamic graph construction, where stock are represented as a node and the edges connected stock based on shared industry classification, market capitalization similarity, or common institution holder. These dynamic graphs evolve over time to reflect changes in the market condition. The integration in the sentimental analysis, We have extracted sentiment data from the financial news and the discussion forum of Yahoo Finance and many more other forums. We calculate the bullish and the bearish sentiment score to capture quantitative market signals. For the advanced graph-based model, we employed temporal graph neural network, which basically captures the evolving stock relationship. We have used a graph attention network, which assign important weights to relevant connection, improving prediction by focusing on the most critical relationship. The workflow of our model is as follows. Since we have the four inputs that we are giving in the order of historic sequence, the description of each stock, we have a shareholders for each stock, and the sentiment data as an input, which then feed into the sequence encoder and to the feature extraction. Once this thing is done, we are feeding the input of the sequence encoder and the feature extraction to the stock relationship graph, which will come under the time-aware graph relation attention network, which then feed into the graph neural network, which creates an embedding based on the stock and edges based on the mutual relationship between them, which then get into the stock market prediction, which predicts the next day stock price prediction and the bidirectional movement. Coming down to our data collection and pre-processing, our dataset includes 6 months of data of 700 different stock in technological sector only, which spans around 18 industries. It consists of the following: historical market data. We are using a daily OHLC prices, which is like high open close prices, adjusted close prices, and trading volumes. We are using stock description, textual description of every company operation. We are using institutional holder data, details of top institution holder of each stock, and the sentiments data extracted from Yahoo Finance discussion between a time period of February 29, 2024 to June 26, 2024. We have applied several pre-processing steps. The first one is linear interpolation, was used to handle the missing data. Min and max scaling for normalizing numerical feature. One hot encoding was applied to categorically variable like industry and sector. Sentimental scores was then aligned with the historical price data for seamless integration into a dynamic graph. As you can see in the figure, we are using the data set of as follows: stock historic price, which is using a stock of 700 different stocks and industries which span over 18. We have stock description documents, which is using a time period of 6 months and the description of 716 different stock. We have an holder data of 215 plus stocks, and the top holder is 10 plus. We are using a stock relationship graph, which is based on the common holders. If the two stock has a minimum of 6 common holders, that means we are creating an edge between these two. We have edges based on common market cap as well. Coming down to our main part of the node embedding technique, we are using two node embeddings, which is node2vec and graph sage, to capture meaningful relationship among stock. So node2vec simulate random walks on the graph to preserve neighborhood structure. Balances breadth first and depth first search strategy has been used to capture both local and global relationship. This method is especially effective for identifying stock with the similar behavior. The mathematical formula for this is like the minimum of log P of NU U, where NU represent the neighborhood of the node U, and U is the embedding for the node U. For the graph sage aggregation-based node embedding, it aggregates feature from the node's local neighborhood, support inductive learning, making it capable of predicting embedding from unseen nodes. By stacking layer of Aggregation. Graph Sage integrates temporal relationship and sentiment data, capturing interdependencies like industry-wide trends and mutual fund holding. The mathematical formula for the graph sage embedding is as follows. HVK, where HVK is the node embedding of the node V at layer K and WK is the weight matrix and is an activation function. The advantage of using graph sage is it integrates temporal relationship and sentiment data very seamlessly, which is covered in the layers, effective in capturing complex interdependencies such as industry-wide trends or mutual fund holding.
While coming to the experimental setup, we constructed the dynamic graphs based on the following criteria. We divided into three categories. One is the industry classification, second one is market capitalization similarity, and the third one is common institutional holder. Industry classification. Stocks within the same industry are connected to capture sectoral trends, and market capitalization similarity is that edges are weighted by the closeness of market capitalization. And here it shows the mathematical formula for the market capitalization, where MI and MJ are the market capitalizations of stocks I and J, and sigma M is the standard deviation of the market caps. And the third one is common institutional holders, where stocks with shared major holders are linked with weights proportional to the overlap in ownership. And the mathematical formula is that common holders of I and J will be divided by the maximum holders. And the sentiment data was processed using tokenization, stop word removal, and limmatization. Sentiment scores were computed to quantify bullish or bearish tones. These scores were synchronized with historical stock prices to create temporally aligned graphs. And the next one is models used and the results. Here we compared several models to evaluate their effectiveness. Traditional models, which are random forest and linear regressions, are served as baselines. And the deep learning models are LSTM networks, which capture temporal dependencies. And the third one is graph-based models, which are TGNs and GATs, leverage the dynamic graph structure. The source which we got the data from is the Yahoo Finance, and the processing is text data was pre-processed using tokenization, stop word removal, and lemmatization, and the sentiment scores were computed using a tool which quantifies bullish and bearish tones for each stock. And the data set consists of 716 stocks, industries of 18, and the time period is of 6 months. And the time frame is between February 29, 2024 to Jan 26, 2024. Pre-processing steps involves handling missing data, normalization, one-hot encoding, and edge weight calibration. And our key findings are TGNs achieve the highest accuracy of 77% with graph size embeddings, outperforming all other models. LSTMs performed well with 75% accuracy. Financial metrics like information coefficient, rank IC, and Sharpe ratio highlighted the model's ability to deliver risk-adjusted returns. And if you see, the GATs achieved the maximum accuracy of 84%. And here we can see the F1 score, precision, and recall for the various models included are in this slide. So the next one is financial performance metrics. To evaluate model performance, we used information coefficient, which measures the correlation between predicted and actual returns. And the second one is rank IC, which computes Spearman rank correlation, offering robustness against outliers. And the third one is Sharpe ratio, a measure of risk-adjusted returns. And here in the tabular form, we have noted down for the various methods, the IC, rank IC, long short average return, and the Sharpe ratio. The TGNs outperformed traditional methods with a Sharpe ratio of 0.55 and the highest IC, demonstrating their exceptional predictive power and robustness. And while coming to the conclusion, In conclusion, our study demonstrates the advanced graph-based models such as TGNs and GATs significantly outperform traditional approaches by incorporating dynamic graph representation and sentimental analysis. We improved both accuracy and robustness of stock market predictions. Our framework provides a competitive edge in the financial forecasting, especially in volatile markets. And the future work will focus on integrating real-time sentiment data and exploring hybrid models that combine econometric techniques with graph neural networks. Thank you, and I'm happy to take any questions.